All right. Thanks all for joining today. And we have today's speaker, Silvia Almada Monter, who is a graduate student at MPIA, working with Max Grunke. And today she's going to talk about her recent theoretical work on escape of Lyman radiation through anisotropic media. So it ended up being very interesting and also has a huge potential to use Lyman-α radiation as an indicator of a Lyman continuum escape, if I understand. And Silvia, please take it away.
Yeah, thank you very much for this opportunity, and thank you very much for listening to my work. Yeah, thank you very much also for the introduction. As you very nicely said, my name is Silvia Almada Monter. I am a PhD student working with Max Grunke at the Max Planck Institute for Astrophysics in Garching, Germany. And today I'm going to be talking to you about my recent paper, but also a paper that we published last year, because those two are together. And yeah, as you mentioned very nicely, I'm going to be talking about the escape of Lyman radiation through anisotropic media. Actually, the name of the paper is Escape of Lyman-α Radiation through Anisotropic Media. But I'm going to be talking a little bit about two Lymans, and this is why I didn't write alpha in here. But well, let's just get to the first Lyman. So we know Lyman-α, it's the transition from the first excited state, and it's in the UV part of the spectrum. And one of the most important things, and the things that I like the Lyman-α the most about, is because it's a resonant line, which means that there are many scatterings, and this makes it a very good tracer of neutral hydrogen. It's a bit tricky, but I will talk about it in a moment. So because we were talking about escape, so the first question that comes to mind is, how does Lyman-α escape? And first of all, to understand how it escapes, I would like to talk a little bit about frequency diffusion of Lyman-α, which basically is just as it sounds, like the frequency that it comes in, the photons comes in, it's a little bit different from the frequency that comes out, and very easily, like with every single scattering, there is a different frequency, and this is one of the reasons why we have double peaks when it comes to Lyman-α emission lines. I also would like to talk about physical space diffusion, which means that with every scattering event of Lyman-α, there is a change in frequency, but there is also a change in mean free path, depending on this change in frequency. So this is very important for Lyman-α escape, because it depends on how many scattering events the Lyman-α photons went through. And then as you go with more scatterings, then there is an increased probability of transmission, because it might be that the Lyman-α photon mean free path became extremely big, and then it could jump out of the cloud, the gas cloud. So yeah, Lyman-α escapes through a double diffusion process, and this is done also through scattering. Okay, so Lyman-α is very important. It has a lot of information, including column density, dust, kinematics, and it's a wonderful probe for the ISM and the CGM. It has a lot of information that can tell us a lot about the distribution of neutral hydrogen. But something that we have to take into account is that astrophysical gas is anisotropic. And I don't think I need to convince you too much of it. But with the anisotropy, it comes some big problem. And the problem is that Lyman-α is not very easy to understand. So there's a lot of data out there. Like in the recent years, there have been lots of observational data from the space telescopes that give some puzzling Lyman-α line profiles. But we have tried in many ways to have a clear theoretical interpretation of Lyman-α observables, but as of now, the attempts to decode Lyman-α have been mostly through isotropic models, that is to say shell models, spherical models, and this, of course, don't really represent real scenarios. So in order to talk about Lyman-α escape and to use it as a tracer for Lyman continuum, we need to take into account the anisotropy of the gas that Lyman-α photons are traveling through. Also, this gives us, because it's anisotropic, this gives us another question that we would like to answer. And the question is, which gas do Lyman-α photons really probe? When we take a look at Lyman-α line profile, which density can we extract from it? So this brings me back to my initial slide, which when I told you that I will be talking about the second Lyman. And then the second Lyman is Lyman continuum, of course. So Lyman continuum and Lyman-α travel through the same neutral gas. So if we can use Lyman-α as a tracer for the distribution of the neutral gas, then this can give us some hints about the conditions that enable Lyman continuum to escape from the galaxies. So this sounds very simple to do, but in reality, it's again very complicated. We might think that since Lyman continuum cannot freely escape because it's constrained by the high density gas, then the only way that Lyman continuum can escape is through some channels, some empty channels or low density channels. And we might think Lyman-α also escapes through these channels. So this gives us another question that we want to ask, and it's how can we connect Lyman-α escape to use it as a Lyman continuum tracers? This is far from simple, and there have been many works and many groups that have tried to do this. For example, one of the most famous relations that we have with Lyman-α and Lyman continuum is the peak separation of Lyman-α and the escape fraction of Lyman continuum. The peak separation is an indicator of density. So the lowest the column density, the lowest the peak separation, the highest the escape frequency. Sorry, the escape fraction. As we can see, it works with these points, which happen to be low redshift galaxies, but it doesn't really work with the ones that are higher redshift galaxies. So it's really not very well understood yet how we can do to trace to trace Lyman continuum using Lyman-α. It's not very clear as of now. And I would also just put a question mark to this part here. So low peak separation really indicates high escape fractions. Well, we wanted to know what were the effects of Lyman-α emission when it comes to having a hole in a very simple distribution of gas. Of course, we know that both Lyman-α and Lyman continuum escape through the same channels, but they, of course, escape differently. So we wanted to know what was the effect and how we can use this to trace Lyman continuum. So we use these models in which we can isolate the physics and check if we can then complicate things a bit further. Okay, so what were we expecting? If we take into account that there is a hole and Lyman continuum just completely stops at the high density regions, but Lyman-α, as I told you, is constantly scattering in the gas, and we expect still most of Lyman-α photons to go through a channel, through the empty space, because for Lyman-α photons, very dense gas is like a wall. So the photons will hit the wall and then they won't be transmitted to the other side. So we basically expect to have large peaks close to the line center and almost no red and blue peaks. In order to get this expectation, we can take some the transmission probability that Neufeld derived in 1990s, and we get that there must be a 4 order of magnitude difference between the central and the red and blue peaks. So what did we get? We got triple peaks. So in a very simple experiment, we got something that we didn't understand. Of course, there are some very rare cases of observed triple peaks. For example, the sunburst arc is the most famous one. There is some flux near the line center, which is expected, but we are not expecting the central peak to be so small. We are expecting something like this, going back to this slide. However, we got this. Of course, there is some puzzle here that we were not understanding, because this central peak should be 4 orders of magnitude larger than the blue and the red peaks. Yet, we see something in the center which is not even close from being 4 orders of magnitude. This is a lot of against common sense. Because it is as if we were expecting also if we were looking through a window, we would expect to see light also coming through the walls. And this is exactly what we are expecting the gas to be for Lyman-α photons, because it's very high column density. Then Lyman-α photons should just crash against the wall and nothing should be transmitted. However, we are seeing some Lyman-α being transmitted through the walls and not only through the windows. This is what inspired the name of our letter, which we published last year, and which is like the first part of the paper that I'm presenting now. So going back to this, maybe we think that there is something that we can do or something we can understand about the transmission in the slab. So we checked it, and effectively, there is a transmission fraction difference in between what we are expecting and what we found in the experiments. There are orders of magnitude, and the transmission is way larger than we expected in the beginning. So in order to understand this, we were scratching our heads for a very long time, and then we came up with the solution which implies solving the diffusion equation with an observer barrier. But since this is a bit confusing for talks, I always like to refer to it as with an analogy, which is the gambler's ruin or the goat. So imagine for a moment that the goat is a Lyman-α photon and the ridge is a very high column density gas. So usually we would think that if the goat is transmitted, then it would just jump out of the slab or of the gas, and then it will be transmitted. But however, most of the photons do not do this. Actually, most of the photons will just jump one step on the left, then 2 steps back, and then 3 steps on the right, etc., etc. And eventually, the goat will just be reflected. So, as I told you earlier, the number of scattering is important for the transmission, because the more scatterings, the larger the chance to scatter until the escape frequency, and the larger the chance for the mean free path to increase, so that it can jump out of the gas cloud. So this is what we did. Actually, we found that the probability density function was consistent with the Levy distribution. And once we did that, we were able to compute the transmission fraction. And now it worked, and it was aligned almost perfectly from our experiments. So this sounds like something that has a lot of impact. So first of all, the first thing I want to say is that Lyman-α photons don't probe only the path of the least resistance. So there is light coming out of the walls. There is also light coming out of the windows. So it means that Lyman-α photon probes the high density gas and also the low density gas. Like what I showed you earlier, not only coming through the path, through the low density channel, but also coming through the high density regions. So this implies that Lyman-α traces general properties of the distribution. This for the connection with Lyman continuum might imply that there might be holes in there, even if Lyman-α line profile does not show them. So in this case, we might expect to see this central fraction to be a bit larger, and then we think, oh, there is a hole there. But in reality, it might be that Lyman-α is hiding these holes. So this might be a reason why we can get large peak separations, but still non-negligibly Lyman continuum escape. So yeah, I mean, we did this, and we tested with many other parameters. Like, for example, we filled up the channel. What happens if this channel is not completely empty, but there is some very low density in there? And we found again that Lyman-α traces both of this distribution, these 2 delta peak distributions. We also did the test with some outflowing gas, and we found similarities with the sunburst arc, which we are already working a bit on. And we also found that one of the effects of Lyman-α, of the holes or the channels in Lyman-α, is asymmetric line profiles. But also something that we did is we tested for log-normal distributions. We put just log-normal distribution as it would be with turbulent media. And Lyman-α photons, again, do not escape only through the paths of the least resistance. So we would have column densities that are low, and we would expect, if we were thinking that 10 to the 22 or 10 to the 21 is the wall for the photons, then we would expect most of the photons to go to the 10 to the 18. So we would expect the peak separations to trace and to probe 10 to the 18. But this is actually not the case. As you can see, Lyman-α photons are tracing the column densities that are more likely to be found according to the probability density function. So actually, one of the main results of this paper is that the peak separations point between the median and the mode of the distribution, not the mean, and especially not the lowest value. So with this, I would like to leave a slide with the most important conclusions, and also this QR code can take you to both of the papers that I have been talking about. So if you have any questions, I'm very happy to answer. Thank you very much.
Thank you, Silvia, for the very nice talk. And I think it's time for the questions, if you have any. Larry?
Yeah, excellent talk. So I presume that these idealized models don't have any dust, and it seems like since the Lyman-α has to scatter lots of times, once you put any tiny amount of dust, it's going to change the line profiles and the, what fraction of it comes from the scattered versus straight through. Have you tried assessing that at all, or?
Yes. I don't have the plot here, but we did try this. It's actually in this last paper that we took out like a few weeks ago. And the result is the transmission through the gas is enhanced. So the transmission, if, for example, we have feedback that could remove the dust from the channel, or feedback that could remove or put dust in the channel. We did this test. And the effect is, of course, Lyman-α is absorbed by the dust. So this effect is a bit lowered, but still is much higher than what we were expecting.
Yep. Other question? Yeah, I have a question. So when you mention about the discrepancy between the relation between Lyman-α peak separation and the Lyman continuous K fraction, that are shown in one of the observational study, probably Carrot et al. And I mean, as far as I know, the relation between the Lyman-α peak separation and Lyman continuous K, one of the strong indicator and strong correlation we know about Lyman continuous K. And so I just wonder why we do not see such a relation from these higher redshifts Lyman continuum liquors. And my question is that, see, what redshifts are there? And also probably that may be resulted by IgM attenuation in the middle. Still, yeah, there are some significant IgM attenuation might shape the observed Lyman-α profile of these higher redshift galaxies, so they might block the relationship between the Lyman-α peak separation and Lyman continuum photon escape. That's kind of thing that I've been thinking. And do you know about that kind of points in that aspect?
Yeah. So this is a very good question, and this is also something that I have been thinking about. Actually, these ones are low redshift, and they fit really nicely. And the reason why I think this is because they are smaller, so we are having a better view of what the global Lyman continuum or the global Lyman-α escape is. Whereas when we see something that is even farther away, it's much more difficult to see. Also, something that might also happen here is that of course, this is not observed Lyman continuum. This is by other means and by other methods, this Lyman continuum escape was inferred. So this can also be one of the reasons of the discrepancy.
What are the redshifts?
These are high redshifts. I don't remember exactly the redshift. I don't have it in the top of my head, but yeah, it's higher redshift. I think it's higher than 6, if I'm not mistaken.
Okay, so completely inferred
This
then.
this paper that's referenced is redshift 3 to 4.
3 to 4.
Okay.
Yeah. I was just looking it up.
Yeah.
Okay.
So the Lyman continuum measurement not directly comes from the observation, so it might be.
Well, for 3 it could, for 4 it's pretty dicey.
Yeah. So there are still some sort of uncertainties out there. One other question is, do you see some line of sight variation? I don't know how you model this on isotropic medium, but when you measure the Lyman-α profile and escape of Lyman-α, I mean, maybe for both Lyman-α and Lyman continuum, do you see the line of sight variation in your experiments?
Yeah, of course. If we change the line of sight, we will see different line profiles. So of course it depends on the line of sight. However, this thing for the transmission still holds in general. So what I mean is, like, of course, we're going to see different things when we take a look at different lines of sight. But the transmission, the transmission at these temperatures is still enhanced. So what I mean is, like, when we take a look at a triple peak galaxy, which are very rare, when we take a look at them, before we used to think that this has to be a very tiny hole or a very tiny channel through which the Lyman-α photons are passing through, so that they pass enough to still allow us to see the red and the blue peak. But with this new transmission enhancement, then it's much easier to allow the path and the channel to be a little bit bigger, a little bit larger. So of course it's going to change depending on where you see it, but this still holds.
Right, thanks. And do you have any other question? Okay, then let's thank again. Stop recording.